we're going to just focus on the sun all the way out. We have a solar corona. And also why the sun has a wind that comes off of it. We'll also lead into what these things are. And the short answer, these lectures are sort of structured with some forethought, is the sun has a corona and a solar wind because it has a magnetic field. That's why the sun has a magnetic field, but we've already discussed that. So the thing about the corona is we have beautiful images of it. So why not start with a nice picture of the solar corona? And this is not an eclipse picture. This is actually made in extreme ultraviolet. You've probably all seen images like this. Those of you who specialize in solar physics are pretty familiar with them, but a lot of other people see them and aren't always sure exactly what they're seeing. So I want to just go through a few basics to carry around in your head. First of all, this particular image, 193 angstroms, is what you're seeing is all the same temperature. So one thing you know, this is 1.5 million Kelvin, the corona is hot. Okay, so at least 1.5 million Kelvin. And it's not simple, it's not a perfect sphere, and so there are places that are dark, there are places that are bright, there are places that are just right, in between. What you're seeing in the variation in brightness is density. Right? The emission is going as the density, the electron density actually, number density, number per cubic centimeter squared. So what you see that's bright has a high density of 1.5 million degrees stuff. Stuff that's very dark has a low density of 1.5 million degree stuff, etc. And what I'm going to try to convince you is that what happens is there's a source of heat in the corona. And that is adding heat to this outer atmosphere of the sun is making it dense. So where there's more heat being added, there's a higher density. Now, in addition to the corona, I put up my two other slides that you saw before. These are exactly the same images you saw before. One of the things I can do with giving all these lectures is I can try to link them. And you can see that where the magnetic field is particularly strong, where there are sunspots, there's strong magnetic field, but there's other places of strong magnetic field. And from that comparison, just by eye, you can immediately see, where there's strong magnetic field, that's where the corona is dense. That's where we have high amounts of 1.5 million degree stuff. So already you should get the suspicion that whatever is creating the heating and therefore creating the corona has to do with the magnetic field. Okay, and we'll get a little bit more into that. The magnetic field is somehow leading to hot material. So we have magnetic fields here, and the other thing that's going to come in is where the magnetic field is closed down, and we'll talk more about that, get more into our spherical harmonics, that's going to lead to even higher densities. All right, now let's get into one of these active regions, one of these places with particularly strong magnetic field, where we have both a positive place and a negative place. So the magnetic field lines there are basically connecting the positive to the negative, and a cartoon version of this would be a little loop like this. Here we're looking edge on, so there's the surface of the sun that's not the corona, and then we have a field line that, because of this MHD requirements, the plasma is more or less confined to stay on this magnetic field line. And what I've argued is there is heat somehow, and we'll talk a little bit more about what that heat might be, heating up that plasma. And evidently there's radiation coming out of the plasma. So the very simplest picture we could have is a 0D picture where we simply say, there must be a balance between the heat coming in and the radiation going out. So this stuff just stays as it is for long periods of time. And if we put this into math, there's an equation in one of your, I should have put this as volume 1, where the radiative losses in the corona come as a result of collisions between ions and electrons. And here I've basically put the product of the densities of electrons and the density of hydrogen. And they depend on temperature because the faster these particles are moving, well, I won't say the faster, the different speed collisions can excite the plasma in different ways. And it's extremely complicated how that happens. Fortunately, it's boiled down into this function that's in this green curve here, plotted on a logarithmic scale. That's 10,000 Kelvin right there, 100,000 Kelvin, million Kelvin, 10 million Kelvin. Okay, so this function of temperature is fairly complicated, and here you see the underlying reasons. When you're at 10,000 Kelvin, there is a lot of hydrogen. There's a lot of hydrogen in the sun. The hydrogen actually has one of its electrons very often, and that makes it a particularly good radiator. As the temperature gets up north of 10,000 Kelvin, that happens less and less often because the plasma is too hot to allow neutral hydrogen, and so there's less emission by hydrogen, and silicon takes over. Silicon can hold on to more electrons because it has a much higher charged nucleus, and so it starts to get excited and radiated at temperatures all the way up to about 100,000. Carbon, what you can't make out here in this yellow, this is oxygen, and then by the time you get up to 1 million, it's really the iron atoms that are emitting. That's why when we look at the sun here, 193 angstroms, this is showing us iron that is 11 times ionized, because that is what is doing most of the radiating at 1.5 million. So that's why it's so bright and easy to observe. But these different ion species, I don't want to go into this. We could talk for days and days about this. But they basically lead ultimately to the rate at which plasma energy is lost. Now, here I've plotted it as a function of density squared times temperature. I want to make this a function just of pressure. And I'm going to argue later on that what happens to the plasma, its pressure is not going to change. It's going to change very rapidly and then sort of stay the same. So during heating or cooling, we might think that the pressure is more or less conserved. And then we have this other function of temperature, which is this green curve divided by temperature squared, which falls off this way. So this is the energy lost per pressure squared. Okay? Now, I want to pose this question. If my heating, oops, I should have, yeah, that's that. If my heating were here, then, oh, and sorry, there's two curves here. One thing is all this atomic physics is very complicated and different atomic physicists get different answers. Here are two versions of those answers, one by a guy named Meyer and another by Yuri Feldman. You can see they're not exactly the same, but they have a very similar trend here. So we'll focus on the green one, say. If I put this much heat in, this many ergs per centimeter squared, second centimeter cubed, then to balance the loss, the gain of energy, I would need, oops, I'm sorry, we're focusing on the green, yeah. I would need the plasma to be about 1 million Kelvin, and the whole thing would be stable. I'm sorry, not stable, in equilibrium. Okay? So that's the balance. Heat in, dash line, radiation out, the green line, they balance there. Question is, what if something happened and this got nudged so it's a little hotter for an instant than it would be in equilibrium? What happens to the plasma? Imagine we have this nice balanced equilibrium, but something knocks it and makes the temperature a little above the million that it would balance at. Go back to 1 million. What happens in this curve? What happens to the amount of radiation you're giving out? Nick has a question. Oh, this is temperature? I should have emphasized it, but this is 1 million. This is 1 million. Yeah. So, and this is the radiation, the heat out, the energy out. And let's just say the energy in stays always the same. But we've gone to a little hotter above the balance. What will happen then to the radiation out? Drops off. So we have a balance, right? Stuff coming in, stuff going out. Stuff going out drops off, but the stuff coming in stays the same. What's going to happen to our temperature? Rise. It's even hotter, which makes our problem even worse. Well, this is why we don't see this. This is the problem you get into with zero dimensions. It's unstable. Right? It's unstable radiatively. Now, if I'd gone the other way and said, what if it was a little cooler, then it actually would radiate more. The stuff going out would be faster than the stuff coming in, and you'll start losing. Right? I knew a professor who used to illustrate this with the problem with bouncing checks, where you don't have enough money in your checking account, and you bounce a check, and then they charge you a fee, which makes your checking account go even more negative, which then causes them to hit you with another fee, and it runs away. It's unstable. So this whole range from about 10,000, 20,000 Kelvin up to tens of millions, we cannot have a stable equilibrium there. Right? The temperature cannot stay there. Because if it were there, anything nudges it, it will fly away even to get too hot or too cold. Known as the radiative instability. So what happens? Well, what we really have to do is go to one dimension. We actually have to say, let's let the heat come in, radiation go out, but also if there's an imbalance, especially if there's too much heat up here, the heat will be conducted using a thermal conduction term that carries heat down the temperature gradient. Right? It goes from hot to cold. This is a very cold region. The heat and the heat will go from the hot part to the cold part, and then we'll also get radiation out of the cold part. The mathematics to describe this, I have basically the same two terms. Here's the heating, here's the radiative losses at constant pressure again. So we have the same curve, but now I have one extra piece here, which is the thermal conduction. And so kappa dt by dl minus kappa dt by dl is the heat flux, and this is the divergence of the heat flux. Okay? And the other thing you can notice here is, once I tell you what this function is, this is, if P is a constant, this is a differential equation in temperature, second order differential equation in temperature. You can go through the exercise of solving it. Here's I've already done that for you. Here's the solution. This is the temperature as a function of distance L along the axis. This is what it always looks like. There's a high peak temperature right at the top, and it falls off. And here I've taken the pressure to be constant, so the density, the electron density, does exactly the opposite. Where it's cold, the density is high. Where it's hot, the density is low. Now, I can take this density and this temperature and calculate in the red here what the radiative losses look like. And you see how it solved the problem it used to have. If I compare the radiative losses to the heating, at the top, I've entered one end of this unstable curve. Namely, my temperature is higher than it should be in equilibrium, and my radiation is less. So I'm basically getting more energy in than I'm getting out. At the feet, where the temperature is colder, I actually am too cold, and the radiation out exceeds the heat in. Okay? So you would expect it to run away, except these two ends are coupled, and I basically have heat that goes from where there's too much heat to places where there's too little heat. And the thermal conduction carries that from the hot to the cold. There's one magic place, which I've marked in green here, where the two balance. And that, the important thing is if you're going to have a place where it's too little and a place where it's too much, there has to be one place where they balance. You'll also see the temperature, this is the heat flux, so it's negative because the heat is moving it's moving leftward here, still moving leftward. It reaches a maximum here because the divergence is 0 here because it doesn't need to balance. But here the heat flux is moving excess heat downward, and then it's giving up and sort of moving less and less of it down. These magic crossing points divide the solar atmosphere into two regions, although basically there's one here, and then there's one region at each foot point, which is represented twice here. These two regions are the corona. The corona is where the heating exceeds the radiative losses. Then there's something called the transition region. That is where the heating does not exceed, where the radiative losses exceed the heating. And thermal conduction is necessary to couple these. It has to basically pass the excess heating from the corona to the transition region. But this, in just simple energy terms, tells you exactly why the sun would have a corona and a transition region. It has to have a corona because apparently the magnetic field is generating enough heat that it creates this very high temperature plasma that's required to move the heat down the temperature gradient into the transition region. And it has a transition region basically because that's where all the heat gets radiated away. A very bright part of the sun is actually the transition region. This is in a zero-dimensional picture of it. Now, I want to focus on, once I have this differential equation, I can actually work out some of these properties. And here are the scalings of how those go. I didn't tell you what the pressure was. If I told you what the heat was, you would find out that the pressure in the loop goes as some power laws involving the heat rate and the length of the loop. Okay? Not terribly enlightening. The maximum temperature here, and this is going to reoccur, actually has to do with that. So it's the pressure times the length to the 1/3 power. The famous scaling relationship. When I have this equilibrium, I have a maximum temperature that scales as the 1/3 power, or I can plug this in for temperature, for pressure. I find that the maximum temperature goes as only the 2/7 power of the heating. This is what I said. If I heat more, it doesn't get hotter. Shows you the deficiencies of English in describing these things. Heat, as we know as physicists, has to do with energy. Hot describes temperature. Okay? So the heating doesn't actually raise the temperature very much. But if I convert that to density and then square it, I see that it will make it a lot brighter. This also shows me that the longer the loop is, the hotter it wants to be. So little short loops, basically because the long loops have to move heat across a very shallow temperature gradient, so they need to make it a long distance. They have to raise the temperature to get the heat out of there. But when we raise the heating rate, we definitely raise the brightness, the density, and we raise the temperature by a little bit. Okay? That's some important scalings there. So when we look at this image of the corona, this is a slightly different image here, what we're seeing is this coronal portion. This is at 2 million Kelvin. There's a little loop here that goes from the positive to the negative. That's just like this yellow thing. And if you have very good eyes, you might be able to make out that that little loop is bright there. If you look at 10,000 Kelvin or 100,000 Kelvin, this is a different wavelength you see from the same spacecraft. But let's not delve into what it is. It's just showing you where the plasma is 100,000 Kelvin. You're just seeing the feet. So where you would see loops there, now you don't see any loops. You just see where the feet are. This is where most of the radiation is coming out. It had to be moved down from the corona in order to be radiated away. We're going to, in many things we talk about, we're going to see these two combine. We're seeing the hot corona. We're seeing this transition region where the heat is being moved out of the corona to radiate away. The real details below there are nasty. So I won't even, it's basically the radiation is much more complicated. The way the ionization happens, much more complicated. So that's the most we're ever going to say about that. The heating, as I said, is somehow related to the magnetic field. There are a lot of models, a lot of people spent their careers trying to know exactly why. This is a talk where I'm going to be above those levels of details, but I will show you a rather famous plot from Alex Pevtsov and company. I believe I'm third or fourth author on this. It shows a bunch of things. This is parts of the magnetic field. These are active regions. This is the whole sun. These are different stars where we know the total amount of magnetic flux. That is magnetic field times area. That is over many orders of magnitude. And this is how bright the sun or star or bright point is in X-rays. And you can see this power is, did I have the power? I don't have the power. It's about 1.1, very close to linear. Basically, wherever you have more magnetic field, you have more temperature. Whatever is heating the corona and raising it to these high temperatures has to involve the magnetic field. Right? You would not see a relationship like this if it was an accidental effect. So suffice it to say, the structures we see come because of this balance between radiation and heating. The heating itself must come from the magnetic field. It has to be the mechanical, electromagnetic energy propagating through the magnetic field being dissipated as heat. I wanted to get back to a thing when we were talking about the fact that the magnetic field on the sun, the strength varies cyclically with solar cycle. And so we see it go up from 1996 when the dipole was the strongest and the magnetic field had totally flipped already. And then it goes through this solar sunspot maximum when the dipole is flipping around, but the field is actually as strong as it can be and back again. This is images of the solar corona made from 1996, 7, 8, 9, 2001, all the way to 2006 again, so right over there. And you can see there's very few of these regions with hot, dense coronal material. And then as the cycle of sunspots increases, we get to this part of this image of the sun full of magnetic field, but also full of corona. We have these situations happening all over with hot, dense loops, and then back down again. If you look at the overall brightness of the sun, and this again, I apologize, is not so, the axes are not so clear. The overall X-ray brightness, and this is made from the GOES satellite, made outside of town here. It's in Broomfield, where they make these spacecraft, or where NOAA commissions them. This is our weather satellite, but they also monitor the total amount of solar X-rays in this bandpass from 1 to 8 angstroms. Between solar minimum and solar maximum, this X-ray emission goes up by a factor of 50. And a field has created that much more hot coronal material irradiating X-rays. There's a really marked difference in these short wavelengths between solar minimum and solar maximum. We'll get back to this again when we talk about the ionosphere. The ionosphere is strongly influenced by the short wavelength radiation. So what happens to the ionosphere is a consequence of how this solar corona evolves over time. And I will get to this on Saturday. This is a blow-up of that portion there. And you see that even as it stays at a certain level, the X-ray brightness will go up by another factor. It's 50 times higher than in solar minimum. And it goes by over a factor of 100 there, but only for, what, half an hour. This is hours. Sorry, these are days, so for half a day, so for 12 hours. This is a solar flare. So we'll get to one of the energetic events is the vast increase in the brightness of the solar corona in X-rays, solar flare. So it's a highly variable process that creates the solar corona, and it creates a solar corona that brightens very frequently, with great intermittency. This is the brightness of the sun over, this is taken from Judith Lean and Tom Wood's plot here. This is a color version. Now, unfortunately, some of these people plot in nanometers because they're not astronomers. And so this is 100 angstroms, 1,000. This is their nice 10,000 angstroms, etc. Here is a black body radiation curve, this dashed line here. This is the surface of the sun at 5770 Kelvin. Has this nice black body spectrum. Falls off like crazy at 1,000 angstroms because this is peaking right around our visible wavelengths of, say, blue, yellow, orange, right? It would be basically 0 if it weren't for the corona. Here is all the emission from the corona and the transition region. The blue is much higher than the red would be. This is the million-degree corona emitting at wavelengths of 100 to 1,000 angstroms. All the emission we see from the corona is from there. In the green is the percentage of variability from solar minimum to solar maximum. You can see over the visible, it's very small. It's 1 part in 1,000 variation between solar minimum and solar maximum. But in the corona, it's well over a factor of 2 or 3. Right? This is the fact that the corona varies dramatically with the amount of magnetic field on the sun. Therefore, the radiation from the corona, which is these short wavelength radiations, all vary tremendously. And they're quite a bit less intense. So, right, so we don't get a lot of energy at these wavelengths, but it's much more than we would if we had a star without a magnetic field and therefore without a corona. Another version. This is the Eve spacecraft, again, built right over at LASP, the University of Colorado. But one other thing that I should mention, because to see the corona, as we'll see tomorrow, you have to go to space. Well, to see the corona's short wavelengths, you have to go to space. It's not true that you have to go to space to see the corona. The corona emits X-rays, but it also emits microwaves. So if you plot, here's just the sunspot number, but we've seen that that's a proxy for how bright the X-rays are. And the emission in 10.7 centimeter microwaves, that is 2.8 gigahertz, see that they're very strongly correlated. If you take an image, and this is actually at 17 gigahertz, shorter wavelength microwaves, you can see all the same features. Now, they're not, I mean, this is pretty cool, but it's not as beautiful as this. It's tough to make these images. I will give them lots of credit for being able to make images in the microwave. All I can make in the microwave is hot pockets. And they actually are imaging the corona, and everything you see in X-rays you see in microwaves. So microwaves are a much cheaper and better way of figuring out how much X-ray radiation is coming out of the sun without building a spacecraft. Yeah. Oh, yes. You're yes. I'm sorry. I will say it's tough to do this. I know that. This isn't simple, and this cost $1 billion. I don't know how much Nobayama has. I bet it's less than $1 billion. Much more affordable. And here is a version of the sunspot number, but it's basically created in green, just using the microwave flux. This is considered by people who really have to understand how much radiation is coming out of the sun. It'd be a much better, more physical way of knowing about the corona than counting sunspots, which is considered by many to be sort of numerology. So you measure the flux of the sun at 10.7 angstroms. It's been done for 10.7 centimeters, sorry. Been done for a long time, and you get something that tells you how much of a corona there is, and therefore how much X-ray, short wavelength radiation we have. So that's the corona in these closed regions, and that's really what you're seeing here, corona in the closed regions, which is why when you get to solar minimum, it's so small. Now let's talk about the open regions, which are basically these regions here, which we call coronal holes. Now there is 1.3 megakelvin material here, it's just at a much lower density and therefore appears kind of black. But if you measure the brightness from there and the brightness from there, they're different by a factor of 100, which means the density is a factor of 10 different. That's not enormous. It's not like there's zero density there. It's just that your eye makes this look very dark. The story here is different for one important reason. The magnetic field lines, instead of closing back down and having 2 feet where they're basically confined and they have to move the heat down by thermal conduction, they open off into space and my heat balance is just slightly different. I have the same heat, presumably, going into these fields. I do have radiation coming out, obviously a lot less. But because it's open, I can also have a flow of material out, if I should choose to have such. That flow will carry energy as well. So I have 2 outflow channels. I have the loss of, well, 3 actually, kinetic energy, which is very small. I have the advection of enthalpy, right? Rho times V times the enthalpy per unit mass, which is written here in terms of the adiabatic index of the gas in general. It's called the specific enthalpy. And that is a heat flux, a loss of energy. Basically, this is where you get the wind chill factor. Parts of the world where the wind chill factor is a real thing. This is why you have wind chill factor, because gas, air will carry heat away. And it will carry heat away very effectively, which is the lesson here. This actually is much greater than the radiative losses. So our energy balance is no longer between heat in and energy out. It's really heat in and, well, energy out through flows. That's why we have a solar wind right there. It's carrying away the heat that we know the radiation was really bad at carrying away anyway. And to do some math with this, the classic analysis, I'll put the heat in, some rate Q, and I'll have the flow go out, and it goes out along these magnetic field lines, where if I just pick a bundle of them, the cross-sectional area of the magnetic field lines is going to vary as I go. S is the coordinate along the field lines. So this cross-sectional area will vary. And the energy loss is going to be rho times V times the area. And then here are 2 of the loss terms I just talked about. This is the kinetic energy. This is the enthalpy flux. I've thrown away the radiation because, as I argued, density is not high enough to make it all that important. And this is actually the gravitational potential energy. As the material flows upward, it's actually gaining potential energy. So its potential energy is going up, and we have a change in energy. If I have balance, then this must balance the heat in, which is Q. Okay? This, though, if I look at it, this is the mass flux. This is basically the amount of material that's leaving. And I have to think in terms of the energy losses, I have a fixed amount of mass coming out of here, and all of these guys have to balance. And actually, this is Bernoulli's law right there. The fact that these 3 have to be a constant is what you learn when you learn Bernoulli's law, that as the kinetic energy goes up, the enthalpy goes down, or as the enthalpy goes down, that is, the pressure goes down, the kinetic energy goes up, which means higher speed, where the pressure is lower, and you have yourself an airplane. Okay. The simplest case to work out, the reason I kept these with the gammas in here, is I can take the limit that gamma goes to 1. This is, I've been arguing that temperature is not a big factor in all of this, and this is basically saying, let's make it isothermal, as if the thermal conduction, the 1D aspect of this, is carrying the heat as fast as it can all along the tube to basically equalize the temperature. Then I have a very simple equation. This basically becomes a logarithm, because as I take the ratio of, I have 1 over 0, but I have something to the 0th power, that becomes a logarithm. And now I have this being constant, the velocity, the sound speed, which has also been a constant now, the logarithm of the velocity and the cross-sectional area. And this piece here is just a function of velocity, and this is just a function of position. So I have a very simple mathematical problem to deal with here. I have some function of velocity plus some function of position is a constant. The velocity is the kinetic energy and the enthalpy, and the position is the area part of the energy and the gravitational potential energy. Bernoulli's law says those have to be constant. This piece here, F, as v goes to 0, this logarithm is going to go to minus infinity, so minus the logarithm goes to infinity. As v goes to infinity, this piece goes to infinity at both ends. It has a minimum, which you can work out is at the sound speed. The other piece, d, minus the cross-sectional area. So as the cross-sectional area gets big, this piece gets small, or as the cross-sectional area gets small, this piece gets bigger. Oops, sorry, I meant to graph. Oops, that. Oh, we'll get to that. Yeah. And basically, as a function of position, the G curve looks like this. It's very small for small radii, where the area is big or small, and it's very small for large area where the potential energy is. I'm saying that right? It looks like this. The most important thing is if I plot this function, which is a function of position and velocity. These are contours of this function. My flow has to stay where these contours are constant. So the flow, as it goes from 0 radius or radius 1 out, and this is velocity, it has to stay on one of these curves. Okay, that's Bernoulli's law, basically. So which curve does it stay on? I should point out where f is a minimum, that's this line here. This is where the velocity is equal to the sound speed. This is Mach 1. So every flow below here is subsonic flow. And one of the things you can see is as subsonic flow approaches a nozzle, approaches a constriction, which is what happens to the cross-section here, it stops. Right? The way you're all familiar with, because you're all familiar with subsonic flows. As you try to pass water through the hose and you put your thumb over it, it goes faster. Okay? That's the way we work when we're in subsonic world. We speed up to get through narrow passages. Supersonic flow does exactly the opposite. It approaches a constriction, it slows down. It passes through an opening, it speeds up. Okay? This is a huge difference between subsonic things and supersonic things. Why when they tried to build airplanes to go supersonic, they faced some real challenges because all the engineers had worked with air that did one thing, and suddenly they had to work with air that did exactly the opposite thing. Not a good situation. Bad if you're an engineer, a lot worse if you're a pilot. So what can happen if I have subsonic flow? It's approaching a nozzle and it speeds up and then it passes through. This is the place where the constriction is a minimum, and then it slows back down. These are subsonic. They always remain smaller than the speed of sound. This would be if I sent it in supersonically, it would slow down approaching that nozzle, get to the nozzle, and then speed up going back out. Okay? So one interesting flow line here is the one that starts out subsonic, and just as it reaches the throat of the nozzle, it gets to the sound speed, and then it's supersonic going the other way. So it's subsonic, it sees something get narrower, it speeds up, then it becomes supersonic, and it sees something widen, and it does what? Stop. It just keeps speeding up. This is the Laval nozzle problem. Here's the simple version of it. If I have a bottle of gas here and I force it out of the throat of my nozzle, then if I'm on one of these subsonic flow lines, I go faster and then back down to slower, and the pressure is very similar here to what it is here. So I will go through that nozzle exactly as fast as the downstream pressure allows me to go. Vent into an area with lower pressure, I will go faster. But only as fast as the obstruction downstream permits me to go. This is the way it works here. If you open a high-pressure gas bottle into vacuum or air, something that has a much lower pressure, then actually you cross that on that transonic flow point and you exit the nozzle going supersonically. And if you're going supersonically, then everything downstream is irrelevant to you. So all of the properties of the flow are determined by that throat. So this curve here is what happens if you have a corona that has high enough sort of pressure, as we saw, high enough pressure that it's basically venting into vacuum. Of course, we could be in a situation where the sun is encased in high pressure plasma that's pushing back and preventing the solar wind from going supersonic. But that's not what we have. It lives in a system where it's surrounded by material that has such low density that it's like opening a high pressure gas bottle into air. It goes supersonically. And once it goes supersonically, the flux rate is determined entirely by what the properties are at this transonic point. That's the solar wind. It escapes at one radius here, it's about 5.5 solar radii, where it goes from subsonic to supersonic and then just keeps picking up speed as it expands outward and the area expands. So first the area is contracting and it's speeding up because the area also includes the gravitational potential. And it's squeezing its way through and then it expands supersonic. So from this you can work out that the solar wind rate has to do entirely with the heating and something that's determined by the geometry. The more you heat, the more wind you're going to get. It has nothing to do with anything downstream, just entirely determined by the heating rate. The density, same thing. This is the way the solar wind is created. It's created by heating down here that escapes through what's essentially a nozzle into a vacuum, and it's going supersonically when it leaves. Okay? And this will always have a lower density, no matter, this is the density at the point where it crosses, but you can track that all the way down here. It will always have a lower density than these closed magnetic field lines. And the reason is because it has an extra mechanism for getting heat away. Not just radiation, but enthalpy flux. Enthalpy flux is carrying the heat away. The radiation is not. Therefore, it has to be at a lower density than the corona, which has to rely purely on radiation. It has to get up to a density where the radiation can do that. Our coronal holes are always faint for this reason. So comparison, we have heat in both cases. Here, only coming out through radiation. So it has to be at a pretty high density in order for that radiation to do anything. Here, heat is leaving through a flow. Radiation doesn't matter how dense it is. And in fact, the density it's at is really set by the density required to give you a mass flux that puts you on that transonic flow line. Okay? Any questions? This is why we have both corona, what I think of a corona, an active region corona of closed magnetic field lines that's dense and therefore very bright, but also one where we have a wind coming out and both of them caused by the heat coming in. Now, all of this is premised on knowing that some magnetic field lines are closed and some magnetic field lines are open. Some magnetic field lines go straight out into the solar wind. And how do we know which those are? Well, we have to come back to the fact that this magnetic field is sort of, its curl is given by the current. And in order to be in equilibrium, that Lorentz force must be 0. A quick way, and I argued sort of more sketchily, and let's just stick with that argument, is to say that there really isn't that much material to carry currents. So the magnetic field in the corona is going to be largely curl-free. I can write it as my favorite scalar potential, which solves Laplace's equation. Therefore, I can expand it in spherical harmonics. Now, I'm going to make one modification. This was actually done without your knowledge last time. I'm going to say my potential has to match the field given by the dynamo, which is what we observed, the field inside the sun and basically reaches right up to the surface. So the radial magnetic field at the surface of the sun, 1 solar radii, is something I know. There is some radius beyond the sun where this wind is basically going to carry the magnetic field radially outward. Okay, so the wind is actually going to generate such strong forces that it's going to be able to make the magnetic field run radially outward. In this simple model, I'm simply going to say, okay, that means my scalar potential must be 0 then. That when I take the horizontal gradient of that scalar potential, I get 0. The field is sticking straight out. So we have a mixed set of boundary conditions. We have a known vertical gradient in the scalar potential down at R solar, and I have 0 horizontal gradients, a Dirichlet condition at the surface. So I have the same spherical harmonics, and I have the same surface radius over R to the L+1 power, the one that decreases with distance. But I actually have to bring in another solution of Laplace's equation where the magnetic field gets stronger as I go outward. That is, it increases with R as a power L. And I have to do this so that when I get to the source surface, Rs, these two cancel and I satisfy my Dirichlet condition. So in the solar coronal solution, I actually have decaying and growing solutions. Well, they only grow out to here, and we don't know. We're going to argue what the magnetic field is outside of this source surface. But inside of this source surface, I'm just solving Laplace's equation this way. Okay? So these are Neumann conditions down here where I've observed the magnetic field. I've already satisfied the Dirichlet conditions. Okay, and again, I can figure out what all these spherical harmonic coefficients are. Here I've called them A instead of G. So if I make one of these maps where I take the solar magnetic field and I unroll it, so I have the magnetic field from the entire sphere unrolled, and here you see 360 degrees of longitude, 180 degrees of latitude. It's done actually, so this is sine of the latitude, cosine of the polar angle. Nice map like this. This is a plot, although slightly different color scale that I showed before. And this I can decompose into spherical harmonics and make the maps that I was showing you before. And this is a cartoon version of that map. This is the place where, at the source surface, the magnetic field is going outward, going inward. There's the place where they reverse. But the internal version of this map, you see, the internal version of this field, you see that you have some of these field lines that are closed, and then some of them are open. And then right where this field on the source surface is reversing, you actually have a field that just grazes it, or comes up and hits it, and then comes back down. This divides the closed field lines from the open field lines. This is everything about why there are bright parts of the corona and why there are faint parts of the corona. There are open field lines here, and in this map, they're all confined to the South Pole and the North Pole. And I have closed field lines that are all along the equator. And this dashed line is basically where on the surface those map to. This all comes from a very simple model. It's an extrapolation, a potential field source surface model. But you'll see a lot, and this is a real image of such a thing. Okay, so there's the sun. Here is, they've basically taken this whole thing over the entire sphere and plotted it everywhere. But you can see underneath these blue curves are all the parts of the corona we expect to be closed and therefore very hot parts of the corona. And then on the northern region and on the southern region are those parts that we expect to be open. And those are going to be the coronal holes. See a different version of this. This is taking this map here and unwrapping it. So there you see on the surface of the sun, this is all the closed portions. There's all the open portions. See, you have a nice extension of the open portion. This just comes from the spherical harmonic expansion. So you can have coronal holes that exist way up close to the equator simply because that's how the spherical harmonics work. Create these boundaries that extend in all places like this. If I map the magnetic field at the source surface, this is the plots we were seeing before, I have negative field, that is field coming in the south, and positive field in the north. It looks much simpler, much smoother than this green region and this red region, because these green and reds are not telling me about the magnetic field strength. They're telling me about where those field lines go, whether they go all the way out to the surface or come back. This is basically generated by this. So aside from delving into the details, it's all buried in the harmonics that I derive out of here. Take the harmonics, I put them into that expansion, and then I learn all of this information. What it looks like on the very surface, if you degrade it a bit, you'll see that these regions correspond to places where there was strong magnetic field, and that's what's creating these extensions here. Because this strong magnetic field is not closing down, it's simply going straight out into the solar wind. So we have open and therefore dark regions there. That's what we have. And get solar wind out of there and out of there. Questions on this so far? Because now I'm going to move out beyond our surface and we'll start talking about what happens all the way out to interstellar boundary. Yeah. Yep. This one? Yeah. The gray is negative, so field that crosses, shoot, I have it better drawn here. It's basically crossing this boundary here, this orange boundary, going inward. So I've again unwrapped it into longitude and latitude, and you can see actually the gray is going inward very strong, and then there's two more bands, and then this is 0. This line here, where the magnetic field is neither going in nor out, that is this point here. The magnetic field is coming in here and going out there. Going out through there, coming in through there, at that point there. And it's not the equator. Right? Some places it's the equator, it crosses the equator. But it's this long line here where you are, if you're on one side of it, you're coming in. If you're on the other side, you're going out. If you're below it, you're actually part of a closed field line that's coming from the north going back down to the south. This is sort of a map, and this is used all the time by people who want to either know what the fate is of these field lines, whether they're going down into negative or positive regions, or from everything we'll talk about from now on, if you want to go outward. In fact, it's called a source surface, even though when you're doing the coronal reconstruction, you actually think of the dynamo as the source of the magnetic field. This boundary here is what people think of as the source of the solar wind. Now we know that's not true. The solar wind is coming from down here. Heat is being added. It's expanding outward, going supersonic somewhere. Actually, it's probably going supersonic out there. But this is the place where if you want to know what the magnetic field is in the solar wind, you can just start from this place here. Tells you that basically if you're in the equator at this latitude here, you're going to see magnetic field pointing towards the sun. If you're here, you're going to see magnetic field pointing away from the sun. Across here, you're going to see magnetic field. A lot to digest here. Closed corona, little bits down here, all the way out to Earth's surface. This is all modeled, at least, to be current-free. And the models work pretty well. I mean, people who do this is a routine. A lot of these I just pulled off the various websites where you see the actual data people are using. This is, it only tells you Carrington rotations, but from July of 1996. Sure. Carried along, yes, yeah. Which no spell checkers seem to recognize. Convection means carried with the wind. Convection means something where there's a driving force, often thermal instabilities, the light stuff being underneath the heavy stuff. Advection just means, I don't know why the flow is moving, but it is, and it's carrying stuff with it. Still vector, it's advection, carrying your heat away. Another 5 minutes. Smoke them if you got them. Oh, yeah. Okay, let's see. Oh, okay. Physicists. All right, sure, sure. All right. So back, and I want to start what we have left from this boundary, fictitious as it is in this model, but somehow it describes something that really does happen, that the magnetic field inside here is trying not to have any forces on itself because it is stronger than the flows that are being carried by it, right? These flows are being channeled outward by the magnetic channels, which are expanding and therefore accelerating the flows. And this magical boundary is where we have to, in our mind, flip those forces around and think, oh, at this point, the flows have been accelerated to a point, maybe they're not quite supersonic, but they are going to be able to drag the magnetic field outward. So before, the field had the flow had to follow the magnetic field because the magnetic forces were very strong here. Well, potentially very strong, and therefore we had to assume that they were zero, had this form. Now, at this point, we're going to flip around and say the flow is just going straight out along the path that it was thrown, and the magnetic field is getting dragged along with them. So this map here is going to show us where all the magnetic field is going outward, being dragged outward by the magnetic field, and then here is where it's going, outward here and inward there. The result, if we look down on it, this is a cartoon version of the same thing. Here are those closed magnetic field lines. There's a boundary here where they reverse. We have magnetic field that's coming outward here. It's getting dragged with the wind, so it should be radially outward. And over here, it should be radially inward. However, the sun is rotating. So when it throws its material outward, it's actually, the material is going straight outward, if you want, in this picture. But one piece of material that's thrown outward it's thrown outward here, drags this field line out here. In the meantime, that source has moved this way. The sun is rotating around this way. So the field lines themselves appear to trace out these nice spirals, okay? Which is very much like the spirals you see if you've ever seen lawn sprinklers, right? They're sitting there turning. I should have provided a movie of this. And you see these beautiful spirals coming out. And you can ask any non-physicist what path those little drops of water are traveling along to make that beautiful arc. And putting yourself in this, standpoint of your average political science major, what's their answer going to be? Raindrops are going, the water drops are going in a nice little spiral. We know that's not true. They're going straight out, and they're just being emitted at different times as that sprinkler goes around that gives you a pattern that traces out a nice spiral. Exactly what's happening here, right? The flow is going straight out, and the field is tracing out these nice spirals as the sun spins underneath it. So from this spiral pattern, known as the Parker spiral, although the actual equation is the same as an Archimedean spiral, but Parker was the one who decided that the magnetic field lines from the sun would have that same pattern. We have a map of what the magnetic field should look like as it's being dragged outward by the solar wind. And all this solar wind material is just going straight out, more or less, yeah, straight out. So, however, and here Owens and Forsyth have drawn the fact that if we were just looking at this equator, we would see places where the magnetic field is coming out, going in, coming out, right? The boundary between outward and inward is not the equator or the ecliptic. It is complicated by the fact that it's generated by all these spherical harmonics. So if you're looking straight down, you will see a sector where the magnetic field is coming out, and then you cross this boundary, and this is looking north-south, so this is, sort of a projected version of this, but you cross into the inward side. So far, so good. This boundary between outward and inward, which extends all the way out, is called the heliospheric current sheet, the place where field lines switch from going out to going in. This is a two-dimensional cut of it. I'll try to show you some better pictures. Yeah? I guess if you went all the way out to the heliosphere, the idea was that they would close back on themselves. this is a source of puzzlement for many people, and it should be. From a practical standpoint, it's not all that important where this thing closes back down. But certainly the same amount of positive flux that goes outward must be coming back in. But it's not required by any law of physics that this field line that goes out ever has to come back in again. You could take yourself into a larger and larger perspective and maybe say there has to be, well, there doesn't have to be an edge to the universe. But by then we're getting very philosophical. So from the standpoint of space physics, we sort of say, it doesn't really matter what happens to it at 100 solar per AU. You can just think of it going out forever. These are field lines. I can just trace a single field line. But I can bundle them together and it will be a bundle of field lines here. Those are going, I'm not sure, there are pictures in the book that show those are wound into little cones, really, in these simplified pictures. The poles are very important. I'll show you some pictures that involve those. And the solar wind coming out of the North Pole, say, is just going to go outward, and it's dragging only outward field with it. So in the simplified picture, if we just followed one of these that was on the rotational axis, we wouldn't have this problem of it being wound into a spiral because it's going straight out, dragging its field line straight out. You could just picture that as a single axis coming straight out and then another one coming straight in. One's at slightly lower latitude, further from, would form little cones, helically wound cones. Regret that I didn't put any of those cool pictures. They're in the book that show all these windings. We tend to be biased towards thinking about what happens in the ecliptic because that's where we live. Almost all our spacecraft are there. And this is showing you a model of that solar wind and that magnetic field line wrapping. And you can see this one has various spacecraft that NASA cares about. Where is Stereo B? Where is Stereo A? Where is Spitzer, etc. This is a practical value just in the ecliptic. All these spacecraft are in the ecliptic. All of these planets are in the ecliptic. So they just give you this ecliptic plane. Here's a picture of what it looks like out of the ecliptic because there is some value to that. But here's that view I just showed you with these Parker spiral, and these dashed black-white lines are the field lines in a model. The colors are the density. And actually, they multiply it by r squared, so it doesn't fall off too rapidly. We'll get to how this thing falls off. But this is the structure of the solar wind. Oh, yeah, wait. Here is where you would separate positive from negative, and if you traced out that current sheet in the fact that not exactly along the equator, so you get this cool, rippled, what's often referred to as a ballerina skirt pattern, where the separation between inward and outward field has this fluted structure. As it is, as I said, the wind is not doing this. It's just dragging pieces of this heliospheric current sheet radially outward, but they're coming from different places in the sun at different times. So it creates this pattern here. This is what happens when you get a sheet that is oriented like that. The wind is all coming outward. The magnetic field is all going outward there, coming inward there, and you get this pattern here. This is closer to this kind of source, where you see that the extension from now positive in the north, negative in the south, the separation is very highly distorted. Here, at solar minimum, it's much closer to being just along the ecliptic. So this is something closer to this. So this is all a consequence of this structure that we talked about in the corona being imprinted onto the wind. And the wind, which was accelerated in ways that we went into great detail, by now is in that supersonic region where it doesn't care what's ahead of it. It's going too fast to care what's ahead of it. It just keeps going out at the same constant speed. So this kind of mapping at one solar radii, we've seen how that maps to something complicated like this. Outward field here, inward field there. Here is that same movie of how that whole ballerina skirt flips itself over. It's very distorted and then just turns itself over. The wind doesn't really care that much about it. And that is all part of the plot I showed before. I had a lot of questions. I didn't explain this very well. The green lines, which are reflected, positive and negative, this is the magnitude of just the dipole moment, which is 3 out of my infinity of multipole coefficients, turned into a vector, and this is the magnitude of that vector. And this blue line is the z component of that vector. The magnitude is never smaller, the z component is never larger than the magnitude, so the blue can never go outside of these green envelopes. It can get very close if the vector is pointing straight north or straight south. That appears to be very close to happening over here, not so close here, far away from being close here, etc. This is when the dipole, and I switched to calling it D, the dipole is pointed downward here, upward here, then back downward. So this would have outward magnetic field in the south pole and inward magnetic field in the north, backwards, backwards again. So this structure of the magnetic field has a lot of important consequences. And I want to just touch on a few of them that are important in other parts of heliophysics. One is cosmic rays. Here is a version of looking sideways. This is that fluted heliospheric current sheet. This is the point when dz is positive, so the magnetic field is outward there, and inward here, the rotation of the sun this way is going to drag this magnetic field backwards. So if it's going outward, it also has a component pointing towards us. Here, it's dragging it outward. If it's going inward, it has a component pointed away from us. That's that structure. There are a population of very high energy particles called cosmic rays. These are created very far away, not in a galaxy far, far away. It's actually mostly in our galaxy, but in the shocks driven by supernovas. And those shocks are called supernova remnants. I don't know why. I would have thought that the thing at the center was the remnant of the supernova, but they have named the shocks the supernova remnants. That accelerates particles. We'll hear from Dr. Ofer how it is that shocks can accelerate particles, but we get particles accelerated throughout the galaxy to very high energies. Here are some of those particles showing energies up to, well, if you're protons, this is a GeV, 10 GeV. I think probably if I can cut it off, it goes up to 100 gigavolts protons. Just horrifically high energy protons created outside of our solar system. They enter the solar system from all directions because the galaxy is all around us. They are going at such high energies, and the solar wind has such low density that they don't even care about the particles in the solar wind. They do care about the magnetic field, which we've just gone through a long discussion of. So they see this magnetic field. They also see that the magnetic field lines are moving outward. So they get deflected by that magnetic field and more or less try to follow it as much as a 10 GeV particle could follow the magnetic field. Big gyro orbits, but it's a big solar system. So they move along with them. So here we have that word again, advected. They're moving outward with the magnetic field. The particles that originated out of our solar system are being moved outward by the solar wind. They also diffuse a little bit because the magnetic field has not the simple structure I explained, but that with a lot of random fluctuations superimposed on it. But finally, they have particle drifts. And there are many classes where you learn all sorts of particle drifts. And I don't want to go through them all, but there's one important one called the gradient B drift. So these particles going around the magnetic field lines, if the magnetic field varies in strength, they don't make a perfect circle, and they basically tend to drift in one direction. The velocity of the drift is given by, this, which if I do a little bit of vector calculus is basically the magnetic field direction crossed with the gradient of the magnetic field. Now there's 2 points I want to make about this. One is we just worked out that the magnetic field points inward and into the page, outward and out of the page here. And the gradient is basically always inward, right? The magnetic field is getting weaker as we go out. So if I work this out, I get B out of the board, grad B, and I get drifts that carry these particles, they have positive sign towards the equator, and these also towards the equator. So in both hemispheres, these cosmic rays are being driven towards the equator. Now, another reason for writing this vector thing this way is it's a curl of something. It has zero divergence. So the drifts of these particles aren't going to create any cosmic rays or destroy any cosmic rays. So if particles are moving towards the equator, there actually must be a flow out along the equator, out along the heliospheric current sheet, and in along the poles. So cosmic rays are being moved inward by this drift and outward by the solar wind. This has a, well, suffice it to say that it's going to allow some of the cosmic rays mostly to come in through the drifts along the poles, and that's only in this case. If I reverse the sense of the magnetic field, B is going to change, B squared is not. This all happens in reverse. So for the other orientation, magnetic cosmic rays will come in along the equator, out along the poles, and all this has the following significance. Here is another plot of the sunspot number. So we have solar maximum here, where what is the dipole moment going to be around solar minimum? Maximum, sorry. High or low? Dipole moment. What? Low. It's going to switch. It's switching from, in this case, a positive to a negative. Then it's low. It's back to positive again. So the times when this drift can bring cosmic rays into the solar system are when the dipole moment is high. Sorry, when the dipole moment is high and the sunspot number is low. So we get high, and this is a plot of our detected cosmic rays, in this case everything above 3 GeVs. We see high cosmic ray fluxes at solar minimum. Again, high at solar minimum, high at solar minimum, high at solar minimum. Right? That's when the dipole is configured to give us drifts that bring these solar wind particles in. This is also one of the only signatures you see that shows you that the solar cycle is not 11 years, but 22 years. When the dipole is positive, we have cosmic rays that stay high for a while. They're coming in along the poles, and that seems to persist for a long time. When it's negative, they have to come in along the heliospheric current sheet, and that seems to not happen for as long. So we have this much more peaked, they call it rounded, peak in the sunspot, in the cosmic ray flux. So we see rounded, level, rounded, level. It really cares whether the dipole moment is positive or negative. because the cosmic rays are going to come in from opposite directions. And during the solar minimum, they're going to have a harder time coming in because mostly the solar wind is moving them out. This has a lot of significance for, say, if you care about the impact of cosmic rays, and this is one of the real hazards if you're an astronaut outside the magnetosphere. This is what you care about, not solar energetic particles, I'm afraid. So if you wanted to go to Mars and not be bathed in cosmic rays, do you go at solar minimum or solar maximum? Solar maximum, right? Cosmic ray flux is low at solar maximum. Counterintuitive. You'd say, oh, all these flares. Like, don't worry about the flares. The cosmic rays are there 24/7. They will do you damage. Last thing, I'll just show you that as the sun changes from minimum to minimum, our sun changes the dipole moment. The wind that's coming out from the poles, is going fairly fast. This is fast solar wind, and it is going 800 kilometers per second. The wind that comes out along here, and there is some wind that's following these field lines here, tends to be a lot slower, 400 kilometers per second. This is a map by the Ulysses spacecraft, comes from figure 8.2, of a point when the Ulysses spacecraft actually flew over the north and south poles, and it measured, and this is basically velocities plotted radially outward as a function of latitude. You see it didn't go right over the North Pole. It went within about 10 degrees of the rotational axis. But you see very high solar wind speeds, very high solar wind speeds. These are the low solar wind speeds that happen when you're at the ecliptic, etc. When you're at solar maximum, the structure is very complicated. It's not a dipole anymore. The solar wind is coming out from lots of different places, and there's lots of different places where it's very close to a boundary. The solar wind is fast in places, slow in others, very complicated. And then here again, and they haven't quite completed their pass, but you see it returning to a similar kind of structure. I think I'll leave it at that. That just sort of gives you an idea of how the solar cycle, the variation in the magnetic field, imprints itself on the solar wind and the way, well, let's just skip to the way our whole heliosphere is basically created by this solar wind. So from the center of the sun outward, we see the density drop off. Here we're going to get to tomorrow. We encounter the, oops, we're almost out. We encounter the Earth in this particular case, and the plasma density goes up there. So we have sort of a source of plasma. Or what's going to happen if yeah, there's sources of plasma. And this is a plot of the magnetic field strength. Again, we have a magnetic field from Earth. And most importantly, the temperature. The center of the sun, when we get to the corona, we heat up again. When we get to the magnetosphere, we heat up quite a bit. This is the place where we know there are sources of heat, right? If you have a peak in temperature, heat is flowing away from it. That means there's nuclear fusion going on at the center of the sun, heat moving outward down to our transition region here, then heat being generated in the corona, then driving this solar wind, then heat being generated in the interaction with the magnetosphere, and then falling off. Our final boundary here are these cosmic rays, which are actually coming inward. And this I drew as a separate set of temperatures. It's much hotter. If we turn those gigavolts into a temperature, it would be 10 to the 12 Kelvin, but it's not a temperature at all. They're just high energy particles moving their way in. So that is the story of why we have a corona and also why we have a solar wind and sort of how that structured creates heliosphere. Rise it, skip over those, you have those. It's because of the heating in the corona. It reaches high temperature because the radiation at high temperature is less effective than at low temperature, and so we get this imbalance problem. We need the thermal conduction, which creates essentially two phases: a cold radiating phase, the transition region, and a hot not radiating phase, which is the corona. More heat leads to higher densities in the corona. The wind is there because instead of radiating, the heat is just being carried outward, being driven outward along open field lines, and that's what creates the helium. Thank you very much. We'll take a half-hour break. Lab. Yes.